Welcome to MIT Inotherm. I'm John Leonhard of the MIT Department of Mechanical Engineering. The Inotherm colloquia cover the leading edge of thermal science and thermal engineering. We have these bi-weekly on a range of topics. Next slide. Today will be colloquium number 15, Dry is the New Cool, Advanced Dehumidification Research for High Performance Cooling. We have a very distinguished panel of experts today, and we'll introduce each of them in detail in a moment. But first, I'd like to introduce our moderator for today, Professor Les Norford of MIT. Next slide. Professor Norford is in building technology, and he is the associate head of the MIT Department of Architecture. He's also a principal investigator in the Singapore MIT Alliance for Research and Technology, the SMART program. His research is in building grid interactions, in building urban environment interactions, in natural ventilation of buildings, and of course in low energy HVAC systems. Les, floor is yours.
Thank you, John, and good morning, good afternoon, and good evening to all who are joining us. Our first speaker is Professor Reinhard Rademacher from the University of Maryland, where he's the Minta Martin Professor. His home department is Mechanical Engineering. He's also associated with the Maryland Energy Innovation Institute and directs the Center for Environmental Energy Engineering. He's the CEO of Optimized Thermal Systems, which provides optimization and design services for companies involved in new products in the thermal sciences. Professional service includes the International Institute of Refrigeration. He's a fellow of ASHRAE and had a long and quite distinguished stint as the editor-in-chief of ASHRAE's research journal. His research interests include heat pumps, air conditioners, refrigeration, software for design and optimization of heat pumps, combined power, heating, and cooling systems, and energy conversion, transport, and storage. Our second speaker will be Dr. Eric Kozabal, who's a senior mechanical engineer at the National Renewable Energy Laboratory. He's been there for quite some time and involved with the Building Energy Science Group. His research in thermal science includes HVAC heat and mass exchangers, and a particular note for us today, work in both liquid and solid desiccants, membrane transfer, indirect evaporative cooling, HVAC and thermodynamic cycles, phase change materials. He's an experimentalist involved in waste heat driven equipment and something dear to my heart, grid interactive control of HVAC systems. He's active in ASHRAE. Forrest Meggers is a professor at Princeton. He has a joint appointment in the Anliker Center for Energy and the Environment and the School of Architecture. He directs the CHAOS Research Group, cooling and heating for architecturally optimized systems. And he's active in their educational programs, including a new PhD track for technology people in architecture. He's formerly involved in the founder of Hearth Labs Thermal Science, Thermal Sensor Spinoff. He was briefly a professional at National University of Singapore, and his education is in mechanical engineering and architecture technology. Research interests include liquid desiccant sorption systems, radiative heat transfer, particularly in indoor environments, geothermal heat exchangers, and building materials. And our last speaker is a longtime friend of mine, Professor Dave Claridge. He's at Texas A&M in mechanical engineering and also associated with the architectural engineering program and director of the Texas A&M Energy Experimental Station. The Energy Systems Laboratory, INTES, formerly at University of Colorado, a group manager at NREL, and a stint of government service in the Office of Technology Assessment. His research areas include energy efficiency in buildings, commissioning existing buildings, molecular membrane air conditioning, which we'll talk about today, measurement and verification of energy savings, and the thermodynamic limits of energy efficiency in buildings. So before we invite Professor Rademacher, I would like to introduce a poll. And this first poll gets at not only the energy implications of moisture removal, but the impact of moisture on indoor health. So what humidity level is best to suppress harmful microorganisms? Votes are coming in. We'll let it go a little longer. Okay, about 2/3 of you voted at slowing down, so I'm going to end this in about 5 seconds. And here are the results. We have a very slight plurality for 10%. The next highest is 50%, and that turns out to be the right answer. As Professor Rademacher will share, there's a competition between mold and virus sorts of things, and 50% turns out to be the sweet spot. So with that, I will invite Professor Rademacher to share his screen.
Yeah, good morning, ladies and gentlemen, and I hope you see my screen and can hear me.
Yes.
Good. So this is an introduction to moisture control for comfort and health. Okay, let me make sure the screen advances, and let me get a laser pointer here. So humidity control, why do we worry about it? 2 reasons, comfort and health. And why? And what is the background information for this? On this graph, you see on the x-axis relative humidity from very low to very high, and on the vertical axis, temperature. You see here that in the lower left-hand corner, and get me the laser pointer here, lower left-hand corner of the graph, we have viruses, respiratory irritation, eczema exacerbation. So in the very dry region and lower temperature region, health is certainly a concern, and that means it represents a bit indoor climates in winter in the Northern Hemisphere. That's why flu infections go up. In the other extreme, high relative humidity, we have mold and dust mites. So these are issues that are particularly prevalent in the summer when it's warm and humid. And the ideal range where viruses and molds and other items are minimized, still present, but minimized, is in the range of 50% relative humidity or so. But you see, these are clouds and they overlap, and it is not a sharp definition. In addition to that, we are worried about or are concerned about comfort. And when we look at the cooler and dry region, the skin often feels dry and brittle and uncomfortable. The other extreme is high humidity. When the temperature is high, we call it muggy and don't feel happy about it. When the temperature is low and humid, we call it clammy, and we are still not happy about it. And again, for comfort, the best region is in the range of the middle range of relative humidity, 50% plus minus 10 or so. So that is why moisture control is important. And now, what are the implications of moisture control in terms of efficiency of air conditioning systems? First of all, the operating conditions of an air conditioning system are pretty much set. And another piece of background information is the temperature difference, the refrigerant temperature difference between the hot part of the air conditioner, the condenser, and the cold part, the evaporator. So when we look here at 45 degrees C versus 10 degrees C, that temperature difference is a measure for the power input. And what we are interested in is the COP, coefficient of performance, which is defined as the ratio of cooling capacity provided by the power invested to get that cooling capacity. So For a typical air conditioning application, the condenser temperature, let's say, is 35 degrees C, assuming it's a 35 degrees C hot day. And we are limited by this temperature. It's determined by the ambient air. We can't do much about this. And it is determined by the design of the air conditioner itself. Now, for the evaporator, conventional application calls for 10 degrees C or so refrigerant temperature. And that is mostly governed by the fact that we need to reduce the temperature of the air that's flowing across the evaporator sufficiently below the dew point to control moisture content so that we end up in the average of about 50%. If you want to increase the efficiency of that air conditioner, the most powerful impact comes from changing that temperature difference. But before we go there, for the typical air conditioner, for these operating conditions described here, the order of magnitude COP is 3. I mean, it varies a lot from equipment and so on, but let's keep in mind 3. When we reduce this temperature interval, the temperature lift, we get higher COP. And considering air conditioning, the first thought that comes to mind is cooling, reducing the temperature. And to cool a space to a comfortable condition, the evaporator at maybe 20 degrees C or maybe 18 degrees C would be quite sufficient to do that. But we would not have dehumidification, and that is a big concern. But if we get away with cooling only, then the COP would be 6, essentially double as large. So that is certainly very tempting to do that and to get to that point. We still need to take care of dehumidification, and there may be better ways of doing it, and certainly many alternative ways, and that's what you hear about in a moment. To round out this picture, to summarize here, to condition air, we want to have ideally, and sorry now the screen is in the way of me, to condition air, we need to have sensible cooling, temperature reduction, and we need to have latent cooling, that means dehumidification. Sensible cooling can be done at a much higher COP than latent cooling. And with latent cooling, traditional design calls for the fact that latent cooling and sensible cooling of air occur at the same time, and that is pulled down to a COP of 3. So the goal of this webinar is to get away from the conventional approach and to take advantage as much as possible that the sensible cooling only has a very high COP by separating sensible and latent cooling, shortly called here SSLC. So how can that be done? How do we go about this? And when we look at a traditional air conditioning system, we have outdoor air coming in, we have a lot of return air, they are mixed, they're going to the traditional evaporator that does sensible and latent cooling simultaneously. And then the conditioned air goes to the space where it gets warmed up and humidified to some degree from occupants and other events, and then is recirculated. If we separate this, one approach would be before the air goes to the space, a portion, and that is typically 30% or so, is branched off. And even if we divide the original evaporator into 2 heat exchangers, the total surface area is the same. And we have a smaller portion of that surface area dedicated to latent cooling only. We still have comfortable conditions in the space. The sensible portion, the air coming off there, is much warmer. So the sensible portion is done with the high efficiency air conditioner COP of 6, the latent cooling with the traditional COP of 3, and we have significant energy savings. We can do the very same, achieve the very same effect by doing it with a parallel design. Latent and sensible heat exchangers are parallel from an airflow point of view, and the energy savings are in the order of 30% when we put it all together. How can we get there? There are other dehumidification options. You see here in the background a glass panel on the backside of which a desiccant solution is flowing down. There's air pulled across that desiccant solution coming out with these muffin fans here. and that does dehumidification only. It is seen as an architectural feature. You know, people say seeing that desiccant solution is a waterfall that provides the image of comfort in summer, while a fireplace would be in winter. It's an architectural feature. Here, calcium chloride solution is used. It's regenerated with solar heat, or can be done with waste heat from an air conditioner, for example, and has the potential for significant energy savings. The more modern version of this is shown in this image with Raschig rings in the background behind that glass panel. Looking at solar cooling, we can do two approaches traditionally. Solar photovoltaic panels with 15% efficiency and the window air conditioner in COP of 3. The solar efficiency of cooling is 0.45. So 1 kilowatt of solar energy provides 450 watts of cooling. Or we can take solar heat with an efficiency of 70%, maybe an absorption chiller or desiccant system. We come up with a combined solar COP of essentially 0.5 as well. Can we do better? Well, first of all, let's take best use of solar energy by having a photovoltaic and thermal collector. Then use the thermal heat to regenerate a desiccant, in this case, a solid desiccant wheel, but could be a liquid desiccant as well. And use the electricity for sensible cooling of the vapor compression system only, which then has a COP of 6. And when we built the system and tested in the lab and applied to conditions in the Middle East, we see that traditional absorption or vapor compression cooling has a solar COP in the range of 0.5. You know, it bounces around depending on months of the year. But the integrated system and letting each component do what it does best, it's a COP that is essentially double as large as that of the traditional approach. Because we have separated sensible and latent cooling and let each technology do what it can do best. On final version here, think about the air conditioner you find in the hotel room underneath the box underneath the window called a PTAC. We have integrated a desiccant wheel for dehumidification and use a condenser heat, the condenser heat on the outside from that air conditioner to regenerate the desiccant wheel. So it takes care of latent heat, latent cooling with the waste heat from the air conditioner, while the evaporator produces cool water, not chilled water, that is in a radiative panel that provides cooling for the space. And this system again has great potential for efficiency improvement. How to do this more creatively, you will hear from the colleagues. And that brings me to the end of my presentation. Thank you very much.
Thank you, Reinhard. If you could stop sharing your screen.
Oh, yeah.
Now, one thing I neglected to do was at the beginning was give us, many of you are familiar with this from attending past sessions, but just the sort of the ground rules of the way we're doing this. So we've heard from Professor Rademacher, and the other speakers will each have about 10 minutes, and then we'll have the discussion. But as we go along, please use the Q&A button in Zoom, and you can take time now if Professor Rademacher's presentation inspired some questions. We'll be pulling questions from that stream and then asking the panelists after they've all had a chance to present their ideas. The questions will be visible only to the panelists and not everyone else. Also, you can submit any suggestions you have for future topics and speakers. This colloquium is being recorded, will be posted later on YouTube, and that posting may also include questions that we don't get to. You can have your questions anonymous if you so choose. So before we move on to Dr. Kozabal, I would like to introduce a second quick poll here. And here it is: to bring Miami outdoor air, which will bring in a ventilation system, to indoor conditions, what percentage of the annual cooling load is for dehumidification? So this does not include internal loads. It's the conditioning of the outdoor air. Thank you for your participation. Most of 73% have now voted. Wait just a couple more seconds. And we'll end the poll here. So something that looks a little bit Gaussian, a majority, modest majority at 70%. And for the brave few at the upper end, congratulations. The answer is 87%, which we will round it up to 90. So some kudos for those at 80% as well. Almost all of the conditioning of outside air in Miami concerns moisture removal. And with that, I'll invite Eric Kozabal to speak next. Eric?
Thank you, Les. My screen's up okay?
Yeah.
Okay. My name is Eric Kozabal, and I'm a senior engineer at the National Renewable Energy Laboratory in the Building Energy Science Group. I like to show this photo because this is a picture of a net zero energy building on campus called the Research Support Facility, a building that's our group is quite proud of, as a lot of things that we research have made their way into this building. I want to acknowledge my colleagues as well, whom I'll be taking some information from, Shuang, Jason, and Omar, who work in the area of desiccant cooling. So I'd like to talk about solid and liquid desiccant innovations, and I'll start off with solid desiccants. You may or may not know what these are. They're typically like solid desiccant beads you can find in packaging. But in HVAC applications, they are impregnated into a desiccant rotor that you can see here, which these rotors become an air-to-air heat exchanger. So this one in front here you can see is bifurcated for the purpose of flowing two air streams through it. And I'll briefly go through some of the basics of desiccant cooling or desiccant dehumidification. So you can think of a desiccant rotor as an RH exchanger, whereby the airstream that you're trying to dehumidify, the process air, comes in and it's the highest RH in the system, and the regeneration air is the lowest, and often much warmer than the process airstream. And so through exchange, we are essentially exchanging RH between the two, and on a psychrometric chart, you can see what that looks like as an example process here, where maybe a saturated cooled airstream is being dehumidified to a more drier but warmer condition. Now, this is an idealized process that I actually often see in product literature, but in reality, and speaking from experience in the laboratory, I can tell you that there are losses in the system, which is shown by not as much dehumidification occurring because of heat carryover by the wheel and heat of adsorption from the desiccant material. I want to touch briefly on desiccant isotherms, which leads into my first research project that I want to talk about. So a desiccant isotherm shows the ability of a desiccant to absorb moisture over the range of relative humidity or relative vapor pressure. A type 1 moderate has often been called the most desirable, but it also is associated with desiccants that have high affinity for water and thus are difficult to regenerate. So silica gel and type 3s are a little bit more common in industry. These desiccants that are shown here are typically stable over a range of temperature. Otherwise, these isotherms don't change over temperature, which leads into a project that Shuang is leading up to. She is working on a thermo-responsive desiccant in which that behavior is changed. So you can see here that this is a hydrogel, a polymer composite with hydrogel that has a thermo-responsive nature in which the isotherm below 35 degrees is relatively constant, and then between 35 and 40, it goes through a critical temperature and can no longer absorb water. So through a laboratory-directed research and development project here at NREL, Shuang is working on the synthesis of a new composite desiccant that does just this. You can kind of see the absorbed and dried out state shown here. And during its dried out state, you can see that liquid water can actually form within the desiccant structure. And if you look at this more or less on a psychrometric chart, you can see as it goes through its critical temperature, the vapor pressure rises. And this is a neat feature of this material because it opens up a lot of opportunities for low temperature regeneration, in which you do not have to heat your regeneration airstream as hot as you would maybe a normal desiccant material. And this leads to more energy efficient design of HVAC systems. I want to quickly transition over to liquid desiccant heat and mass exchangers. I want to point out that there are many types of liquid desiccant heat mass exchangers, or LDHXs. Most common in the last century have been these two fluid packed tower systems where you have an outside cooler and then you have a high flow of desiccant over a packed bed. But starting around in the late 90s and 2000s, there's been innovations in more 3 fluid and 4 fluid, and I'll call these internally cooled liquid desiccant heat exchangers, that allows you to separate the need for a high flow desiccant. You slow the desiccant flow and you use a secondary fluid to pull the heat out of the exchanger. So quickly over the process, or maybe the anatomy, this is what I'm showing here is a desiccant plate structure and liquid desiccant heat exchanger technology that we're working with 7AC technology and Emerson, whereby they are making stacked plate heat exchangers. And you can see here that a coolant flow goes through the middle of the channel. Air is flowing past this exchanger, and water vapor is being absorbed in. And this is done because there are desiccant weep holes that allow desiccant to flow behind a vapor permeable membrane. And when water vapor goes in, the heat of absorption is collected by the cooling stream and carried away. And likewise in the regeneration process, the process is reversed and you're able to desorb here. So you would supply a strong desiccant to a conditioner, and as it absorbs moisture, it becomes weak, and then it becomes regenerated over here, and then becomes strong again, completing the cycle. And this is all put together through a water chiller that's supplying the chilled water and hot water supply to drive the cooling process. So what this looks like on a psychrometric chart, if you're beginning with an outdoor air ventilation situation, your regeneration process streams start at the same point. Your chilled water and your purple vapor pressure of your strong desiccant is your driving potential. And you're able to drive down effectively in one heat exchange step down to or approaching this point on a psychrometric chart. So this opens up a great possibility to avoid extra heat exchangers, as well as pull down the or reduce the need for overcool, reheat, things of this nature that can be energy intensive. And then likewise on the regeneration side with the weak desiccant, you're driving to up here to regenerate the desiccants. And lastly, I'd like to talk about a project that we've been working on for over a decade at NREL here. You may know this as liquid desiccant evaporative cooling, or desiccant enhanced evaporative cooling. I don't want to go into how this particularly works, as we have several publications that I'll point people to. However, I do want to point out that this is a separate sensible latent device, and that it has a first stage dehumidifier that dries the air down to a low dew point from 1 to 1.5 shown in here. And then a second stage indirect evaporative cooler that is effectively a dew point cooler that brings you down to the temperature that you desire. So you may choose a 50-degree Fahrenheit or 10 Celsius dew point, and you can approach that temperature coming out here. Now, this is the main energy input is due to the regeneration of the liquid desiccant. So typically we have been thinking about this in terms of thermal regeneration of the desiccant. But more recently, we are investigating ways of electrically regenerating the desiccant such that we're not reliant on a thermal source at the site to drive the process. This is a project that we are working with a small startup company called Blue Frontier. And the idea is this: you have an electric input into a heat pump, and the heat pump generates heat either by a refrigerant or hot water stream into a desiccant dryer. This is that three fluid exchanger. We use an ambient air sweep gas to pick up the evaporated moisture, and as it goes through the evaporator of the heat pump, we're able to recapture some of the water that has been evaporated and feed that back into the evaporative cooling process. Now, the very neat thing about this is now it opens up the ability to store energy, in a sense, in the form of a tank of liquid desiccant salt. We are using this salt in itself is a project that we're working on, and we're looking at effective electrical, equivalent electric cost of $18 per kilowatt hour. And thus we've created a device that can be charged when electric prices are cheap, and then discharged when during peak cooling. So I want to touch on the efficiency real quick. So thermal regeneration, if you're looking at a metric called moisture removal efficiency of just the regeneration process in terms of kilograms per kilowatt hour, so kilograms of water removed from the desiccant per kilowatt hour of heat, the energy input, thermal regeneration is here down at 1.2. The electrical regeneration process we're proposing is roughly 5 times higher at equivalent concentration of desiccant. And then if you look at this compared to theoretical maximum, which is dictated by the dilution heat of the desiccant, we're approaching 40% of theoretical maximum efficiency to be able to regenerate the desiccant. And then lastly, I have here a graph that has 5 different scenarios. The bottom scenario is a baseline vapor compression load that's consuming about 10 kilowatts during a peak humid day. And you can see if you use this process and regenerate from 12 to 4 a.m., you can shift a lot of the energy towards nighttime, and during the day, reduce the electric draw from the grid by about 80%. We also did some runs where we did regeneration at different times of the day, so you might want to do from 10 to 2 during peak solar or photovoltaic generation. Or you may want to spread it out and still maintain a late evening reduction in power. So with that, that's the end of my presentation.
Thank you very much, Eric. And if you could stop sharing, please. And that was great. A lot of good detail there, and I'm sure it'll spark some questions we'll get to at the end. Before we hear our third presentation, I have one last poll for us. And here we go. So based on what we've heard, the question is, if we separate the sensible latent cooling using desiccants or membranes, as both speakers have mentioned, what are the benefits of this? Improvements in latent cooling, sensible cooling, or both? We're getting a great response. I'll wait just a few more seconds here. All right, we'll close the poll now. 3/4 of you have voted, which is terrific. And here are the results. As a group, we've been paying attention, and the choice of 70% is I think what both speakers have brought out, that not only can we improve the efficiency of removing water vapor, but that allows us to do the sensible cooling in ways that also have higher efficiency. Lower lift, as Professor Rademacher talked about, higher temperature phase change for refrigerants. And with that, Forrest, you're up, and feel free to share the
All
screen.
right. Fantastic. Thanks so much, Les. I enjoyed the questions. Later, you'll all receive your own psychrometric chart to go through and become experts in dehumidification. Today, I'm going to try and present a few building application-oriented uses of desiccant. And first, I'd like to thank, of course, my team in the CHAOS Lab, and as well as collaborators. We've been working with people on other applications, which I won't present, but just mention atmospheric water harvesting is another potential use for technologies like the great TRHC materials that Eric just presented on. And I'd just like to thank the previous presenters for doing a wonderful job of setting us up, setting me up for this presentation on cool buildings with less cooling, where I will be talking about how we've used novel liquid desiccants to enhance and benefit integrated radiant cooling systems. So to start off, a quick overview of buildings that I think are cool and not cool. The tower on the left, of course, the World Trade Center, is conventionally cooled with a large centralized air conditioning system blowing around cold air. The building that I used to get to work on before the pandemic, the Andlinger Center at Princeton, had radiant cooling panels, which arguably provide more high performance cooling and better comfort. But there's a challenge, right? Although these panels, right, can cool and directly provide comfort to occupants in spaces without having to blow air throughout the entire building, they face one significant challenge, which you're probably aware of, which is that we don't like rain indoors. And if I cool the surfaces of my building below the dew point, then I get condensation and rain inside, which is bad. And so if we want to have efficient radiant cooling, we have to find a way to make sure our air is dry enough. And therefore, we need to understand a little bit about the psychrometric chart. The controls that we could conventionally use in that World Trade Center tower, or the vast majority of our office buildings, are built around the psychrometric chart, which, if you didn't know, was also invented by Willis Carrier when he invented the air conditioning machine, as it is a design condition map for air conditioning systems. But I would argue that it's not necessarily the only comfort map, and we will come back to that. because of course we can design how to dry our air very precisely using the psychrometric chart, but it's not necessarily the only way to dictate comfort in terms of our radiant systems. So today we're going to talk about some alternative ways to do that sensible and latent cooling that you all demonstrated you're well educated on. And above here you see an initial prototype that we'll get to at the end of the presentation that relates to how on the right here we're starting to rethink how the psychrometric chart can be informed by alternative mechanisms for keeping people cold. So you've already had a good background on sensible and latent systems and their dependency on temperature, right? Again, I mentioned the radiant systems have a higher temperature. They deliver cooling at the point of occupancy. And also that delivery of cooling there is arguably more comfortable, as you all may have experienced sitting below a diffuser in a classroom or office where you're freezing, but everybody else is getting the nice mixed air. And arguably radiant can provide a better distribution of temperatures for comfort. But what Reinhard very eloquently described is that the COP of all of these systems are inherently dependent upon the temperatures that they operate. And here our radiant panel, again shown in the thermal image here, is operating around 19 degrees Celsius compared to a conventional cooling coil that would have to be cooling air down to say 8 degrees Celsius to dehumidify. And so by doing that temperature increase, we can achieve up to double the COP of the system for delivering that sensible cooling. So remember now we're still need to address the challenge that the radiant system is only delivering that sensible part of the cooling and is susceptible to problems of condensation when we don't deal with the latent side. So how do we dry the air? Well, as we mentioned, it's a significant portion of the cooling demand for outdoor air supply. This is what it takes to dehumidify or to cool outdoor air on the left. It's the majority being the latent cooling, and it requires this very low temperature, again, that is the largest portion of the energy needed to deliver cool air to buildings. So that brings us to, as Eric has already given a great overview, desiccants. And as I like to say as a mechanical engineer myself, that we've generally brute forced the chemical engineers aside, and the vast majority of our buildings use mechanical dehumidification with those cooling coils I just showed, condensing water out of the air with very cold temperatures. So desiccants, they can keep your seaweed from Trader Joe's dry, but also ideally our buildings. And I want to take you through a couple different applications that we've investigated specifically for desiccants. The first one being one looking more on the material side. So how to play with desiccant characteristics to enable novel systems for dehumidification. So as again, Eric already showed, there's different types of desiccants, and we were specifically interested in what it would mean to look at some of these type 3 desiccants where they can absorb strongly, but only really at high humidity flows. But if you remember back to our first question, we're really only aiming to get to 50% RH. So the fact that it's really easy for both these type 1 and type 2, easier for these desiccants to be regenerated, perhaps we should consider them. And the other advantage is the one that we eventually found was that it was non-corrosive. So one of the big challenges with desiccants like lithium chloride are these strong salts that absorb water very strongly out of the air, is that they tend to have challenges with being corrosive and having to use special materials in the systems. So we were supplied with a kind of interesting silicone oil, alkoxylated siloxane byproduct actually from Dow Manufacturing. And the interesting thing is it had really good kinetics, but it had a very low percent uptake. So it doesn't actually absorb very much mass per unit volume. But as a liquid desiccant, that just means we might have to pump it a little bit more. So we went ahead and set up an experiment to see again just how fast we could get water out of the air. And what we found was that, this was a counterflow experiment. There's a tube where air goes one direction, the liquid desiccants flow in the other direction. And we're looking at exactly how much moisture we can remove from the air. Because remember, to be honest, we don't really care what the amount of water that goes into the desiccant is, because that's not affecting our comfort in the end. It's how dry we can make the air. So as long as the desiccant can dry the air, we just have to pump enough to do that. And one of the fun sort of chemical engineering aspects, being a mechanical engineer, was fun for me, was recognizing how diffusion changes significantly. So we have a membrane that contains our liquid desiccant, but is very, very conductive to water molecules. So the water molecules can jump through the membrane very quickly. And when the desiccant comes in as very dry, it has these sites right at the surface that allow the water molecules to jump into the desiccant very quickly. But what happens, and this is common for many desiccants, is that there is a diffusion limitation. So the diffusion into the bulk media of desiccants is often very slow. This is also the case for the salts. And so what we were interested in is looking at characterizing exactly how fast, when we first expose the desiccant, how fast does the desiccant absorb moisture? And it's about twice as fast before you end up in this diffusion limited regime. And it goes to actually more than twice the longer you wait for the diffusion to happen. So we set up an experiment to look at exactly how long in that counterflow tube inside of a tube exchanger, how long can we go and maintain that high rate of uptake? And we found that we could double the kinetics of how fast we remove moisture out of the air if we would limit the distance that it would travel for those tubes to 10 centimeters. But then again, that's a very short space, and obviously we're not removing all the moisture we need to. So what we did was developed a way to disrupt that clogged boundary layer. So we basically took the 10 centimeters characteristic length that we found in our experiment and developed a sort of laminar mixing system for these small tubes. And then to finally arrive at sort of the applied result is once we had that framework of how much, what is the rate we could remove moisture from these sections of counterflow exchangers, we put in a simple energy model for the Singapore outdoor air conditions with about a 0.5 meter by 0.5 meter cube. And we're able to show that it only took about 30 watts of pumping, which was the most surprising result because we had suspected the fact that our low mass, low capacity desiccant would require excessive pumping. But in fact, with just 30 watts of pumping, we could, and it was actually smaller than the fan power needed to supply the air that a single office would need. So for around 130 watts, we could supply the latent cooling that would typically require about a 1,000-watt air conditioner for an office. But again, we still need the sensible part. So we estimated, though, when we would add in the separate sensible radiant cooling system, we could reduce energy by over 50%. So there's a lot of work left to be done, though, and it was already mentioned how we do the desorption. That needs to be integrated into the system. As Reinhold mentioned, you can use the heat rejection from air conditioners. We're also looking at solar panel, standard solar panel to regenerate the desiccants. So a lot of interesting questions around the material science. And now I want to jump back up to the building scale. So that was a fun project around how you can re-engineer sort of the subsystems around desiccants. And now I want to talk more about how we can rethink sensible and latent systems, because desiccants allow us to separate that latent component to cool people, not rooms. So what are we really cooling? Back to our lovely buildings and rooms that we have. We're not actually cooling them, right? A room can't be comfortable. Even if someone says, this room's uncomfortable, I always tell them, no, you are not uncomfortable. Because what we want to think about is how that sensible and latent delivery of cooling to a space is actually interacting with the bodies in the space. And dryness and air movement are two components that are often missed when we only look at the psychrometric chart. And this goes way back to 1963. So I recommend all engineers, all engineers should have at least one architecture book, and that's this one, where they're looking specifically at all these different metrics. And by and large, this is because in 1963 there weren't a lot of buildings that had central air conditioning yet. And so here's a little homework for you. You can go to our little website, ashray.cool, that my student Eric Teitelbaum built, and you can play with how you can map radiant temperatures and or airspeed. So you can look at how radiation and convection affect the human body. So there's a human body energy balance behind this. And what this chart allowed us to do is sort of step out and explore how we can design systems that might manipulate the radiant and air movement aspects independently of our conventions around central air conditioning. So very briefly, one was on the radiant side. We recently built this pavilion in Singapore which took the idea of radiant heat transfer and contained it inside a panel, right, where the panel had this transparent membrane. In the back there, you saw the spectroscopy analysis that demonstrates exactly how thermal radiation goes through these membranes, which can actually be opaque. It's kind of fun, the difference between infrared radiation and visible radiation. And then inside that panel, right, we contained our cooling pipes, which now are only touching dry air that the desiccant inside is allowing us to keep dry. And so now the hot, humid air doesn't actually touch our cold panels, and they can cool below the dew point and allow us to actually cool outside. This is an outdoor pavilion in Singapore where we made it, although inside that space it was 90 degrees and 80% humidity, people still felt like it was 70 degrees. And that's because the desiccant allowed us to keep the surface dry inside. Another alternative one that we might think about doing is how actually just drying the air also can be an important tool for increasing the effectiveness of air movement in a space. So we have a project that was recently funded by the Department of Energy. I'm actually collaborating with Les and Eric on it. It's a very exciting opportunity where we're looking at how we could insert liquid desiccant and vacuum membrane systems, which you'll be hearing coming up next from David, to dry air as it moves passively into a building. And so you can see some embodiments here where we're looking at how a membrane liquid desiccant combination can be built into a window panel potentially, or a vacuum membrane system can create a folded system to allow the vacuum and or the liquid desiccant to have lots of contacting area, the same way the weave of a screen might, and absorb air as it comes into a building, and how that might be integrated into a facade. And so we have these two embodiments we're looking at. We've already talked a lot about liquid desiccants, and you'll hear more about vacuum membrane systems coming up. And we're basically interested in how you might integrate these two embodiments into a section that would go into a facade. And the advantage of directly working at the facade on the drying level is that we have the ability to potentially take advantage of wind, and increase the amount of air movement, again, right at where the user is. So instead of being back in a central system, we can have it right at the facade. And potentially what this plot shows on the right is as I reduce the relative humidity and I have some air movement in the space, the equilibrium temperature that a person would feel, again, this comes from playing with this psychrometric chart, people would feel comfortable, their bodies would be at equilibrium at higher air temperatures. So they're accepting of much warmer air temperatures as the relative humidity gets dry, which if you've traveled to Arizona in the summer compared to New Jersey, hot and humid summer, you might recognize obviously how humidity challenges your ability to accept heat. So this is sort of a very early stage project. We have built this initial sort of window prototype here where we're able to remove 3 grams per kilogram of moisture from air that's just being brought in from wind alone. So that's already an interesting finding. And that would, again, enable us to increase the air temperature in the space significantly. So there's a lot of questions remaining around how we might regenerate these systems, but these are just some ideas and provocations to start thinking about how we might integrate some of these technologies directly into buildings. So with that, I'd like to thank you and just give you a few takeaways. Ideally, one, that desiccant systems are an excellent sidekick for radiant cooling, that there's alternative pathways of analysis around kinetics that chemical engineering offers when we're looking at liquid desiccants particularly. And then finally, just that comfort is not really just about conditioning enclosed, sealed spaces. And on that last note, just to point out that we should all be appreciative of the ability to bring in more fresh air, as much more fresh air as possible, and desiccant systems and membrane systems that you'll be hearing out from David all offer much more efficient ways to manage that latent and humid loads that are in the outdoor air, which is the main obstacle that currently buildings face if they really want to increase outdoor air during summer conditions in the face of things like COVID and disease transmission challenges. So more fresh air is easier, again, with these new novel technologies. So with that, I thank you very much for the attention and my colleagues for their great presentations. I'm looking forward to David. Thanks.
Oh, thank you, Forrest. That was super. So if you'll stop sharing, we'll tee Dave up. Dave, no more poll questions, so take it away.
Okay, so I guess I'll try sharing screen here and then move the one that we want onto here. Now we can find our slide show up. Okay, are you seeing my screen now?
Well, it's a presenter view. If you could go full screen on the,
Oh, right. It ended up yeah, just a minute. Somehow, I don't know why I put it on here.
then it,
So now it's putting it's putting things in the wrong screen.
David, when you go up to display settings in the menu on the very top,
Oh, okay, here we go.
click duplicate slideshow.
There we go, thank you. Okay. Okay, well, we're going to talk, as Eric mentioned, about a different type of membrane dehumidification, and I'd like to acknowledge various faculty colleagues who've been working on this. Also, the support from DOE ARPA-E, Department of Defense, and the Navy for the work. And note that both the system that we're talking about specifically and some variants on it are covered by 7 different issued US patents and 20 different international patents. So the system we're going to talk about is fundamentally one where we basically start off with some humid air coming in and effectively run it through something that looks an awful lot, I mean, not in schematically here, we're showing is looking very much like a bunch of air handler fins. And so it goes through the fins, but the fins actually have hollowed out inside so that the fins are each coated with a membrane that passes water vapor and not air. And so then we take and pump out the water vapor from sort of what we'll call the inside of the fins, and we'll go into more detail on that later on. And so in going through basically about 4 inches of this type of membrane fin, 4 or 5, whatever, at typical air handler speeds, we can remove about 50% of the moisture in the air. So then we take this low pressure water vapor, which is typically in the neighborhood of 1 to 2 kilopascals. We put it through a quotes compressor, take it up to 4 to 8 kilopascals, where we can then condense it. At those pressures, we can condense it with typical either anything, whether it's cooling tower water or air condenser, and so we get liquid water that we can pump up to atmospheric conditions. There's a little bit of air leakage, and so we have to have a vacuum pump both to initiate the vacuum and also to get rid of the air that leaks through. Now, to look at the membrane itself in more detail, there's more than one membrane that can be used. The primary one we've been using is one developed by Lou at Pacific Northwest National Lab. And it basically, if we start off here on the left, you have a very thin membrane, about 2 microns thick. It is mounted on a porous metal substrate that's about 50 microns thick, purely to provide mechanical support for this thin selective membrane. The membrane itself has lots of pores in the crystalline structure. These pores are about 3.5 angstroms or 0.35 nanometers in diameter. And without going into the details of how they operate, they're capable of basically passing a lot of water vapor and virtually no air. In fact, most of the air that leaks through the membrane generally appears to be going through crystalline defects in the structure. So if we look at what we sort of talked about as our air handler fin earlier, if we view this as our fin, where we have membrane on the outside, both sides of the fin, inside we have a hollowed out area where we can remove the water. And so the air simply passes by on the outside. Typically we'll assemble it where we have, of course, lots of different fins, just like we do in particular air handler cooling coil, and so it's going into membranes on both sides of any given air passage through it. It is a very effective dehumidifier, basically at constant temperature. Also note, of course, that it does not involve the use of any kind of desiccant. And so that is a way in which it's different. It performs in some sense the same function, but it's a different way of getting at it. Now, if we look at an ideal version of the system where we have perfect membranes that don't leak any air, and we look at a system like this, and we have our vapor compressor, and we have our vacuum condenser and our water pump, and we get our liquid water out, just to look at what the primary energy inputs are. If we had an ideal compressor, it simply has a work requirement equal to the number of moles of water vapor that go through the compressor, the gas constant, the absolute temperature times the logarithm of the pressure difference of the pressures of the inlet and the outlet for our compressor. So that is really the major, for an ideal system, that is almost all of the energy that's required by this system. Now, of course, we have a water pump down here, and so we do have some energy that goes into that pump, but that energy is far less than 1% of the energy that goes into the compressor, so we will typically ignore that energy. If we look at how this system performs, and in this case, we're just going to compare it with the standard vapor compression dehumidification, so we're not comparing it here with the membrane systems and some of the others that we've looked at. We're saying that if we have a Carnot system and we took 94-degree air at 52% relative humidity, which is just sort of a Houston design condition, and we took that air and we dropped the humidity anywhere from 5 to 25% on our chart here, 100,000 CFM of that air with a Carnot system, removed 25% of the relative humidity, or about half of the humidity, it would take a little over 100 kilowatts. With our membrane system, to do the same thing, it would take a little over 50 kilowatts. If we go down to removing only 5% of the moisture, or 5% of the relative humidity, which is, in this case, about 10% of the moisture, why the membrane system gets down to less than 5 kilowatts, while our Carnot system would require about 16 kilowatts. And so it fundamentally, since it avoids sensible cooling, is a very much more efficient in those situations. Now, of course, the real system is going to have a number of things that degrade its performance, just as standard air conditioners do. First one that I'll note is that the membrane size and the water permeance are important, because if you have a small membrane and it's not very permeable, you're not going to get very much water vapor through it. Then when you combine the size, you have a large one, but if it has a significant air leakage, well, then the larger the membrane, the more air that's going to leak through it, and hence the more air that you're going to have to take up atmospheric conditions, which significantly reduces your overall efficiency. And then, of course, we're going to have a non-ideal compressor, and we're going to have a non-ideal vacuum pump. These are things that we tend to have in our regular refrigerant-based systems. We're going to have a non-ideal condenser. We're going to have a pump or a fan, or perhaps both on our condenser. If we have a cooling tower, we'll have both a pump and a fan that will have some parasitic energy. And then we'll have some air pressure drop in the membrane module. Now, of course, that's something that we're going to have in our standard air handler. So that's fundamentally, while we're dehumidifying, we're basically replacing our air handler coil there. Just to look at the ones that are specific to the membrane system, it turns out that if we had a perfectly ideal membrane, and we looked at the percent humidity removed for the conditions we were talking about, we would have COPs that range from above 60 to about a little over 20 over this range. If we had 20 square meters of membrane per ton of dehumidification capacity as measured at this 25% humidity removed, why, it would be virtually the same as the ideal line. We go down to about 10 square meters per ton, why then we see that it starts to drop the COP appreciably, but still actually significantly less than a lot of the other factors that we'll talk about, or that we could talk about, but don't really have time to go into today. Now, the air permeance can have a huge impact. And here we are using units that are, say, 10 to the minus 9, and this is kmols per square meter per kilopascal of pressure difference per second, so it's not going to mean a lot. Let's just say that in terms of a membrane like this one right here has about 10,000 times higher water vapor permeance than air permeance based on the membranes that we're using right now. And there are the membranes we have right now are basically operating in this range. So we see there is a lot of room for improvement in COP from improved membranes. And actually some of the laboratory produced membranes at this point are approaching the region up here, so that we believe over the next 4 or 5 years that it will be possible to have membranes that will get up much closer to this ideal line. So in terms of where the system stands at this point, we have operated a very small laboratory prototype. We have this prototype shown here that is something on the order of a half ton or 1 ton of refrigeration capacity. It has a very low COP at the moment, primarily because of two factors. You see these condensers we used were just some truck radiators, and we threw some box fans behind them. We put some efficient fans on there. That will help significantly. But the bigger thing is that in scaling up to get to the membranes that we needed for this system, why the membrane assembly ended up causing some leaks, and we have figured out how to fix that. They just haven't been fixed yet. But if we fix those leaks, why then this COP will go from 2.1 to 5. And so we will have something that is a dehumidification system that is operating rather efficiently. In terms of just a comparison with a half kilowatt per ton chiller and 100,000 CFM of airflow that we were talking about earlier, with the membrane properties that we have today, what we're sort of denoting the 2020 situation for removing 25% of dropping the relative humidity by 25%. We're at a place where we're using just a little bit over half. We're reducing the energy by 65% by 2025 with the membrane properties we expect then. It will be, I'm sorry, I said 65, it's 40% now, it'll be 65% reduction by 2025. And as noted earlier, down at lower removal percentages, why actually the comparison with the chiller becomes even more favorable. In terms of looking at all of the total parasitics that you have with a regular chiller system, typical efficient chiller system today has about a 0.5 kW per ton chiller. Right now, our membrane system with a slightly improved compressor would be about 0.59, but the 2025 system should go down to about 0.27. And then your chiller system, you're going to have a primary pump and a secondary pump. You don't have that in the membrane system, but we'll have our condensers. So we're saying the condenser and the cooling tower all going to be the same, air handler energy, so that the total plant COP for our 0.5 kW per ton with good components today is about 4.6. The membrane system is close, but not quite there. But if just performing its dehumidification function can be combined with the much more efficient chiller system, just providing the sensible function, as it's been noted earlier. And by 2025 or so, we expect this 4.3 to get up to neighborhood of approaching 7. So with that, I think we'll wrap up and hand it back to Les.
So Dave, thank you very much, and thanks to all speakers. I thought it was a lot of hope for more efficient, sensible, and latent cooling in the future. And Dave, it's great to see something actually built and tested as a system. We have some questions, and thank the members of the audience for sharing them. So we'll have time to get through a few of them. The first one is this maybe for Eric. Others can chime in as well. How realistic is it to use lithium chloride salt as part of cooling systems, with lithium batteries becoming more and more important in our lives, and lithium being a much less abundant resource than many expect? Wouldn't it be better to use more abundant resources? This is particularly important if this desiccant usage in cooling becomes common.
Yes, that's a great question. I would say that right now we're not resource limited, but to follow up on that, we are working with desiccant alternatives. Obviously, Forrest described an alternative desiccant he is working on. We are also looking at potassium-based ions instead of lithium, so potassium acetate as an example. And there's others in the industry working on ionic liquids that are completely an organic ion set, so, or ion pair. So there are lots of material options being developed now to replace lithium because of its growing expense and corrosivity issues that kind of come along with it.
Eric, while you're unmuted and in answering mode, here's another one. Are thermal-responsive desiccants, like the one you showed, the hydrogel, cost-effective at scale? Also, has their life cycle, cyclic life been explored?
Sure. So Shuang Cui here at NREL is really the material scientist on this project. So, and she right now is in the material synthesis phase of this development of this material. So I personally cannot comment on the ultimate cost of this, and I probably defer to her. I think I put her contact information in the slides, or I put it in the comments as well if you want to reach out directly to her. She might have a little bit more information on costs.
It's a relatively new material. I'm working with Sujit Datta here at Princeton on developing some materials, and most people are synthesizing on the order of milliliters of this stuff right now. There's a group at Texas, if you Google the work, and there's another group at Washington, I think. So yeah, look around. It's a relatively low, what we call TRL level now, but I think it's definitely huge potential.
Great. Forrest, while you're online, and thank you for sharing your family in the background there.
Welcome to the Zoom world.
Yep. Couple questions for you. How can we modify the psychrometric comfort map to adequately and intuitively account for radiative temperature?
Well, I very rarely hear the word intuitively with the word psychrometric chart ever put together, but for those of us that have to deal with the psychrometric chart regularly in humidification and cooling systems, the challenge really is how many dimensions can you fit on one chart. And so obviously we tried to do this by adding a contour map. It's again requires more abstract thinking to be able to leverage that. So you have to understand that we're basically mapping. The contour map represents how much we have to radiatively cool or heat somebody to maintain the same human body equilibrium state. And so behind that model is like an assumed physiological model of how heat is transferred between your body. And that's why if you go to the tool, you'll find variables for skin wettedness and metabolic rate in the background. So those two things significantly change what happens at your body. So obviously we didn't talk about sweatiness, but I bet you've all experienced the fact that you're sweaty in Arizona dries very quick compared to sweat in the hot, humid climates, I'm sure.
Well, speaking of sweating, here's another question. Could you get condensation on, for example, clothing when in a high dew point environment with radiative cooling, i.e. in your Singapore prototype?
Yes. it would be hard due to the fact that your body is always producing heat, so you generally push yourself above it. Although I loved Reinhard's comment about the sensation of clamminess, which is when your body is too cold, so your capillaries constrict and your fingers get very, very cold, and they actually approach the dew point temperature, and you feel that weird clammy sensation. But no, in a hot environment where even in the midday of Singapore, just a moderate amount of solar heat and your body heat generally keep your surfaces above it. The interesting thing, though, I will point to is our radiant temperature sensors for the measuring the radiant temperature in the pavilion we built actually did end up getting condensation when we ran the system to very cold temperatures. So in that way, there are other surfaces that don't have internal heat gains that we still do have to be cognizant of how the radiant heat transfer could push those surfaces below the dew point. But it is a very sort of magical sensation to stand in such hot and humid conditions. And you don't have the clammy sensation. You just have this strange, cool feeling.
Okay, here's one more that's just come in. We're on a roll here. Dr. Meggers, isn't personal comfort better achieved with fabric design versus building space design, while attention to both factors is required?
Yes, I wish I was a fashion designer. There are some good examples. Other Lab had a project with ARPA-E building some clothing. Also, the Center for the Built Environment at Berkeley developed a comfort chair. And all of these things are places where you're manipulating more directly at the human scale, like at where people are. But generally speaking, tracking where people go is a big challenge. And so, and having people wear very particular clothing types is obviously more of a social challenge, I would propose. Whereas if we can integrate these into our building systems, there's still a level of mechanized control that we can put in, right? But if there are novel materials that can be easily controlled and manipulated at the body, there's certainly interesting research to be done in that space. And I would also point you to some of the radiant transparent clothing I think Shenhui Fan from Stanford has developed. So there is definitely interesting questions that lie outside of the building domain.
Eric, if we could come back to you for one, how do you deal with the corrosion issue and potential crystallization of liquid desiccant? We acknowledge that some of them are corrosive.
Sure, yeah, I think there's a lot of ways that companies that are dealing with the issue. 7AC, for instance, is using lithium chloride, so that is non-compatible with most metals or metals that are cost-effective anyways. So they concentrate their technology on the development of plastic heat exchangers. In other cases, less corrosive desiccants like the potassium acetate are being developed such that metals can be used with these desiccants. However, the downside is they're not as great of a desiccant as lithium chloride, but the trade-offs seem to be well worth the research.
Thank you. Dave, maybe one or two for you, and we'll beginning to run out of time here. One is, how do you explain having a theoretical limit higher than Carnot?
Well, okay, that's very, very simple here, because remember the Carnot system is having to remove more energy, first of all. But secondly, this is not a heat engine. And so that it no longer has, we're not dealing with the Carnot system. I mean, if you look at things on a purely enthalpy basis, why the Carnot limit and the limit for this system tend to be very close together. They tend to differ slightly, but they're very close together.
And a second question, is your membrane AC system only realistic, both in necessary scale and cost, for large buildings?
No, we don't. I mean, I would say that in terms of scale, I mean, early on it's going, I mean, the membranes are expensive, but Once we get membrane production up and component production up, we expect the cost to be quite competitive. And I mean, if you talk about it in terms of, I mean, with the kind of, people often say, well, gee, it's a lot of membrane area. And so how do you, isn't that going to make it bulky? It turns out that the way you can package the membranes and want to package them, it takes about 1 cubic foot per ton of refrigeration capacity. And if you look at the size of a 1 ton unit, why 1 cubic foot fits inside that very easily. So we see it as having the potential to work in basically any size range.
Great. Reinhard, I have one for you, and this is mine. You showed a number of very thoughtful systems that would improve efficiency. What's your feeling about, I don't know, best approaches for, say, the global south, where cooling loads are increasing exponentially in India and elsewhere? The standard solution seems to be split systems, which do not separate sensible and latent cooling. In, say, the medium term, what do you see as advances that are sort of affordable and packaged enough to be used in at very large scale?
That is a very interesting question, and I think the challenge may be even larger than this. The IEA says we have 1 billion air conditioners worldwide in operation right now. Order of magnitude wise, 2050 it will be 5.6 or 6 billion air conditioners. That is more than an air conditioner for every 2 people alive. And I think we will do that in very different ways. And right now we are thinking about air conditioning predominantly as cooling. In the future, I suspect it may be predominantly much more in terms of humidity control, or maybe comfort, and where the trade-off will lie, as Forrest or others pointed out, I don't really know. So the way we do comfort control may change dramatically and may involve a mix of clothing and, in my mind, a lot more dehumidification and maybe air velocity. The ceiling fan that also cools slightly may be the ideal component to live with in the future. And no idea where that will go, but there is a huge room for creativity and new approaches.
Oh, thank you for that thoughtful answer. We're about out of time, so I would like to share the screen and return this to Professor Lienhart to wrap up. So here goes.
Well, thank you, Les, and thank you to all of our panelists for a really excellent and stimulating set of presentations and conversation. Our next webinar will be on November 10th. It again involves membrane separation for water, but in this case, it's about thermal desalination by membrane distillation. We have an excellent panel for that session. In fact, I'll moderate it myself. Next slide. To wrap up, please type in your suggestions for topics that we might use. You can put them in the Q&A. We encourage you all to sign up for our email list. Again, these are bi-weekly events. You can sign up by going to the inotherm.mit.edu page, and there are links there. We will post this webinar onto YouTube. We'll also post the Q&A, including questions that we might not have been able to get to this morning. So on behalf of the organizers and behalf of the panelists, I thank everyone who joined us today, and we look forward to having your participation in future Inotherm colloquia.
Well, thank you all. Thank you for joining us. Thank the panelists very much. And with that, I'm going to close the session.
Thank you, everyone.
Thanks.